Hello, today I'm going over defining the atom lecture. So this is just an introduction to kind of the history of how we've thought about atoms. And it goes all the way back to the Greeks, at least as far as we know. So let's get started here. All matter is composed of tiny fundamental particles called atoms that are invisible to the unaided eye. So these are super tiny. No matter how good your vision is, you cannot see an individual atom or even a small collection of atoms. An atom is defined as the smallest unit of an element that maintains its unique identity during a chemical reaction. So for instance, an atom of gold behaves just like 10 pounds of gold chemically. If you break a gold atom into smaller bits, which you can, it does not act like gold anymore in chemical reactions. Despite being unable to observe these particles directly, early scholars were deeply intrigued by the concept and proposed various theories regarding their structure. These intellectual foundations allowed scientists to develop complex models of the physical world based on logical deduction. Democritus was a Greek philosopher who lived from 460 BC to 370 BC and was one of the first individuals to suggest that atoms exist. So they couldn't see atoms. This was just more of a thought experiment. Is there a certain unit that is so small that that's as small as you can get? And that's what he was thinking about. He proposed that these fundamental particles were both indivisible, so it couldn't be broken up, and indestructible. So indestructible meaning, again, that you couldn't break them up. While his core ideas aligned with modern scientific theories, they failed to explain actual chemical behavior and lacked experimental support. So again, at this stage, it's just a thought experiment. But he was, right to a certain point. We do call these things atoms, the smallest units of what we can see occur during chemical reactions. This brings us to John Dalton. And this is more current, right? John Dalton revolutionized the field of chemistry by transitioning the ancient concept of the atom from a philosophical idea into a rigorous scientific theory. By meticulously studying the mass ratios of elements as they reacted to form compounds, he provided the first experimental evidence for the existence of discrete particles. So here he knows the masses of these units. He's got two things here that each have a mass of 1 unit. But then he's got this bigger thing over here that has a mass of 16 units. And so it's tracking these units of mass and how they always stay the same throughout these chemical reactions that he was able to start putting data into this idea of the atom. This empirical approach allowed him to bridge the gap between observable chemical changes and the hidden behaviors of the microscopic world. His resulting framework posits that all matter is composed of indivisible atoms which remain unchanged during chemical processes. So these hydrogens are the same hydrogens here, and they're the same hydrogens over here. They haven't changed. These atoms serve as the fundamental building blocks of life, where each element possesses unique properties and atoms of different elements combined in fixed simple ratios to create new substances. Ultimately, his work established that chemical reactions are essentially the reorganization, joining, or separation of these permanent, indestructible units. And he would always get 18 mass units in these equations when looking at a molecule of water. Just an example. Okay. The smallest possible unit of an element that retains its distinct chemical identity is known as the atom. So this is a review. We've already said that before. We know that the atom can be broken down into smaller things, but it just will not act chemically as that atom's type would. So you can take a carbon atom, break it down into simpler particles, but it no longer acts like a carbon atom. Using a copper penny as a scale, one can visualize how even a microscopic speck of dust contains a staggering number of these fundamental particles. In fact, there are trillions of times more atoms in a single coin than there are people living on the planet. This immense density highlights just how microscopic these building blocks are, as it would take 100 million of them lined up to span the distance of 1 centimeter. While atoms are far too small to be seen with the naked eye, specialized tools like scanning tunnel microscopes allow scientists to observe them directly. So that's what this is, where you can actually get an image, although it doesn't exactly look like a photograph, but you can still image individual atoms. These advanced instruments provide the capability to not only view individual atoms, but also to manipulate and arrange them into specific patterns. And we're going further and further with this concept. We're getting better and better at manipulating microscopic items like atoms or like compounds and arranging them at that microscopic level, putting them where we want them to be. This level of precision at the nanoscale opens the door for revolutionary breakthroughs in electronics and medicine. By building devices at the atomic level, researchers aim to create highly efficient computer chips and new technologies for space exploration. Okay, I hope this helped. If you have any questions, please let me know.